Hi everyone, this video looks at the circular motion topic for A-level physics. It covers radians, angular displacement and angular velocity. We will also look at centripetal force and acceleration and consider a few examples of circular motion that will often come up in the exam. If you want to get the free PDF presentation and question sheet for this topic, along with lots of other resources, click on the link in the description. Enjoy the video. So the first thing we need to consider with circular motion is angular displacement. So we could use degrees, which we're very familiar with, but very often we use radians. So you may have come across these possibly at GCSE, but certainly if you're doing maths A-level. So we do need to know the definition, which is written here. So 1 radian is the angle subtended at the centre of a circle by an arc of length equal to the circle's radius. So it's quite a complicated word, subtended, but it's quite useful because it basically means this angle here. So if we have an arc length here, which is equal to the radius, then it's the angle between here of this little triangular segment here. So 1 radian is approximately 57 degrees, and you probably know already that we have 2 pi of these in 360 degrees. So remember that pi is a number, 3.142, so it's 2 times that. So it's not a round number. It's quite, this is why we use pi. So we have to convert between degrees and radians. So if we're going in this direction, we need to either multiply by 2 pi and divide by 360. So what we're doing here is we're getting rid of the degrees by divided by 360 degrees, and we're multiplying by the equivalent of radians. So this is our conversion. So sometimes we just do half of that, and we multiply by pi and divide by 180. So you definitely need to be confident with converting between degrees and radians to degrees. So I recommend you pause the video and just have a go at some of these here before you continue. So let's have a look. So 90 degrees. So if we have nice easy fractions, simple fractions, then we can leave pi in the answers, or we could write this as a decimal. Normally, because physics is a practical subject, we would think about significant figures and decimal places, but it's normally acceptable because pi is a very recognized number to write this as pi over 2, but we could write this as a decimal as well. So that's obviously half of 180, so it's going to be half of pi. So 30 degrees is 90 divided by 3, so that will be pi over 6. So again, if we have a nice simple fraction, we can leave pi in the answer. But if we have something which is not a simple fraction, then we'd have to use our conversion here to get a decimal answer. So we multiply our 174 by pi, divide by 180, and we get 3.04. Going back the other way, so converting into degrees, then here we've got pi, so oops, where's this? This isn't working, one moment. Yep, so if we're converting into degrees, so we have pi, so that is half of a circle, so that's going to be 180 degrees. Pi over 3 is going to be that divided by 3, which is obviously 60. So again, if we have simple fractions, then that makes life a bit easier. But if we have an actual decimal, then we're going to have to use what we have here, our conversion. So it's going to be the opposite of this. So it'll be multiplied by 180 and divide by pi, and we should get our answer of 43. Okay, so let's look at the relationship between angular displacement and angular velocity, and also this very useful little formula here. So you may have come across this before. Theta is equal to S over R. So what we're saying here is the angular displacement is going to be related to the size of the arc length. So obviously as S gets larger, then theta will get larger in proportion. So we can derive where this comes from, and we'll do that in a moment. But generally we can just use this relationship, which is very helpful. Angular velocity, so that's a very important term, given the symbol W or omega. So that's defined as the number of radians per second. So this is why radians is quite important. So our first formula, omega is equal to delta theta over delta t. So that is basically the algebraic equivalent of what we have here. So theta in radians divided by time, that will give us radians per second. Okay, so that is a formula given in the formula booklet. We can also write this as 2 pi f, and we can link these two formulas together if we wanted to. So again, if we're talking about the number of radians per second, if I know f, which is the frequency for one complete circle, one complete oscillation, Then if I multiply that by the number of radians in one circle, that will give me the number of radians per second. So again, we can define this one, omega is equal to 2 pi f, based on the definition. The final formula we have here is v is equal to r times omega. So that's the linear velocity. So the velocity at a particular point, the velocity tangential to the circular motion, will be equal to r times omega. Again, nice simple formula. So we should be given all four of these in your formula booklet, so just double check that your specification provides these. We're not expected to derive them, but we can do, and we may do that later on in the topic. So for example, this first one here. So if we know that the arc length is related to theta, and it's going to be proportional in size, well, the arc length is going to be a fraction of the circumference, and that will be the same fraction as theta is a fraction of 2 pi. So s divided by the total circumference, which is 2 pi r, will be the same as theta divided by 2 pi. So if we work out the arc length, that will be the circumference multiplied by this angle as a fraction of 2 pi, so theta over 2 pi multiplied by 2 pi r. 2 pi is going to cancel, and we have r times theta. So we can derive this. That might be useful, but most specifications would not insist that you do that. Right, so we have a few worked examples. I recommend you pause the video and have a go at these. So get your calculator out and a pen and paper. And the answers are here. So let's have a look at the first one. So question 1, it says we're given s, which is the distance, the arc length around the circular track. We're told the radius, and we're trying to find the angular displacement. And very often it will say radians and degrees, so we need to be able to convert between the two. So we can see it's going to be this first formula, theta equals s over r, and it's just the ratio of the arc length, 150, divided by the radius, 50, so that will give us a nice number of 3 radians. Bear in mind that radians, there's no actual unit for radians because it's a ratio of lengths, but sometimes just to remind us that it is angular displacement, we could write RAD for radians. Sometimes more of a maths thing, they write a little c with superscript, but yeah, we would normally write RAD in physics. And then we can convert it by multiplying by pi and divided by 180, and you should get 172. Question 2 says find the angular velocity if we have 30 minutes for every full cycle. So here we're going to use v is equal to, no, we're not. We're going to use this second one, omega is equal to delta theta over t. So all we need to know is the time period. So we could work out the frequency and use 2 pi f, but we're going to use this one here. So in one complete cycle, we have 2 pi radians. So the angular displacement is 2 pi, and the time period is, well, we're given there 30 minutes. We could write it in as radians per minute, but we would normally use SI units. So 30 times 60 will give us radians per second, and we get this fairly small number here of radians per second. Angular velocity, and now we're given the frequency of rotation. So we could again use the one we've just used, but it would make more sense to use 2 pi f. So again, we know 2 pi is the number of radians in one complete cycle, and we're told the frequency of rotation is 0.42 per second, or 0.42 hertz, or 0.42 cycles or revolutions per second. So we just multiply 2 pi by our number here, and that will give us 2.64. S to the minus 1, we could write radians, even though that's not actually a unit, just to remind us that we're actually talking about an angular displacement here. And question 4, using the final one, v is equal to r times omega. So we are told the radius is 4 centimeters. So the radius of the CD might be larger, but the radius of the point we're interested in is given as 4 centimeters. And we're told that it's rotating at 430 RPM. So you're probably familiar with, you've probably heard of RPM, revolutions per minute. So we'd have to convert that into revolutions per second, or radians per second. So 430 revolutions, so multiply by 2 pi would give us the number of radians per minute. And then we need to divide that by 60 to give us the radians per second. So that's our first thing to do. And you would be expected to work with RPM and convert that into radians per second. So the final stage, we're trying to find the velocity, the linear velocity. So we can just multiply the radius. So we could convert that into meters, 0.04 multiplied by the angular frequency, and we get 1.8 meters per second. And as we would expect, the velocity will increase with the radius. So even though the RPM, the angular frequency, stays constant, as you move further outwards from the center, then the velocity will increase in proportion to the radius. So let's look at the idea of centripetal acceleration, sometimes called centripetal acceleration. Now you might have heard of centrifugal forces, and that is related, but that's not actually what we're talking about here. So we never really refer to centrifugal, we talk about centripetal. And we have to get our heads around this rather strange statement here. And very often exam questions will ask you to explain what's going on here. So an object moving at constant speed in a circle is accelerating. Acceleration at constant speed. This sounds like it's a contradiction, but we have to understand, well, what do we mean by acceleration and what do we mean by velocity as well? So if you imagine we have, imagine an object moving in a circle, then we've got an object here, and we have a velocity in this direction, and then the direction changes. So because velocity is a vector quantity, then the velocity is changing. So that's part of the explanation, the idea that we've got a changing direction of velocity. Also, we have a force towards the center. We'll talk about that in a moment. There will be a resultant unbalanced force, therefore there must be an acceleration towards the center. So it might be a tension is acting towards the center, but there's nothing balancing that. And we need that tension, that resultant force, to change the direction of velocity. So again, if we refer to Newton's second law, F equals ma, if we have a resultant force, we must have an acceleration. And then it's always directed towards the center. So these 3 bullet points here are very often the answer to a 3-mark question in the exam to what is meant by acceleration at constant speed. So very, very important. Now we need to look at as many examples as possible to understand what is providing the centripetal force in every case. If something moves in a circle, then something needs to provide a centripetal force. So if we have a car going around a circular path, around a bend, then there'll be the friction between the road and the wheels towards the center. If we have a satellite in orbit, then the weight caused by the weight due to gravity is providing the centripetal force. An electron orbiting a nucleus, there's an electrostatic force of attraction, which is providing the centripetal force. And we'll look at this next lesson in more detail, the conical pendulum. This is very often the subject for an exam question. So we have an object moving in a horizontal circle, we have a tension in the string here, and this will provide a horizontal component which gives us the centripetal force. So we need to understand centripetal acceleration and also centripetal force. Fortunately, centripetal force and centripetal acceleration are very, very straightforward formula. Now, some specifications ask us to derive these. On the particular one I teach at the moment, you don't have to derive it, but it might be worth looking into, perhaps. Either way, we're given this in the formula booklet. So F is equal to mv squared over r. So this is not only important for this subject, this is really useful for other subjects as well. Certainly gravitational fields, which you'll be studying soon after this topic. And later on, when we look at orbiting charges, electric fields, certainly magnetic fields, then this is a really important formula. And if we can accept that, then we know that Newton's second law, F equals ma. So if we just look at what remains, v squared over r is the centripetal acceleration. So we could calculate, if we know v and r, the acceleration, and if we know the mass, we can find the centripetal force. So a simple example here, and you might get questions this simple. Certainly at part A of an exam question would just be calculate the centripetal force. So if I know the mass, and I know the velocity, and I know the radius, then I can calculate mv squared over r, and we get our centripetal force. Bear in mind that very often we have to explain or describe what is providing the centripetal force. And as we mentioned briefly a minute ago, if we're looking at a car going around a corner, then by turning the steering wheel, which turns the wheels, that generates an additional friction force between the road and the tyres, or the tyres and the road. So we actually have a Newton's third law pair here. And the one we're interested in is the force acting towards the centre. So that's the friction force of the road acting on the tyres towards the centre of the circle will provide the centripetal acceleration. Let's look at a really typical application of circular motion. So this is a mass moving in a vertical circle. So we've got a ball on a string which is moving in this vertical plane here. So normally we need to consider the forces acting at the top and the forces acting at the bottom. So let's consider at the top. So we always have the weight acting downwards, mg, and we also have the tension in the rope. So when it's at its highest point, the tension is pulling it down towards the centre. And at the bottom, slight variation, the weight still acts downwards, but at the bottom the tension is once again acting towards the centre, and that should make sense. So the tension on the string is always pulling it towards the centre. So we need to think, well, how do these two forces combine to give us the resultant force that we call centripetal force? Now this is really, really important. Very often students get confused and think that centripetal force is another force which appears out of nowhere as if by magic. It's not, it's just the name that we give to the resultant force which arises out of the existing forces. So there's only two forces, the weight and the tension, but at the top they combine together. So mg plus t will give me the resultant force. And we can see at the bottom then the tension and the weight are acting in different directions. So the tension has got two jobs to do now. It's got to balance the weight and also provide a resultant centripetal force towards the centre. So Fc, the resultant force, will be T minus mg. So this is really important, the idea that the centripetal force is the name we give to the resultant force which arises out of the existing forces. And then either they combine together or it's T minus mg at the bottom. So we can see here that at the bottom, because the tension has got to overcome the weight and still provide a resultant force, then the tension is going to be largest at the bottom of this vertical circle because it's got these two jobs to do. Let's look at one final example in this video, and then the second video in the series we'll look at several more examples and some more difficult scenarios as well. So this is Ferris wheels. So as I said at the start of earlier on in the video, you need to consider as many different applications as possible so that you are confident with understanding what the forces are, which direction they act in, and how they combine to make the centripetal force. So let's have a look at a Ferris wheel. So at first glance it looks very similar to the previous example, but it is slightly different. So let's have a think about at the top. So the weight always acts downwards, that's fine. Now we don't have a tension pulling us towards the centre as we did with the object on a string. Now because we're moving a lot more slowly and because there are people sat on chairs, then if someone's sat on a chair, then there's a reaction force acting upwards of the chair on the person. So that's actually acting upwards rather than the tension acting downwards, so that's slightly different. However, at the bottom, while the weight always acts downwards, the reaction force is still acting upwards. So actually at the bottom, this looks very similar to the object in a vertical circle where the tension was acting upwards. So this is one of the challenges, and why you need to be really confident with lots of different examples, is there are some similarities, some differences, and very often students get extremely confused with what the forces are and in which direction they're acting. So the resultant force, which is the name we give for the centripetal force, at the top is equal to the weight take away RT, the reaction force at the top. So that's slightly different to what we had before. If this was the tension, it was tension plus mg, because the tension was acting downwards towards the centre. However, at the bottom, that looks very similar to our previous example. The reaction force has got two jobs to do. It's got to balance the weight and also provide a resultant force towards the centre. So with both of these examples, example 1 and 2, you may well be expected to do you will be expected to do numerical calculations, and there will be some examples of that if you go to the PayHip site and have a look at the online course. Well done, we've got to the end of the first video of circular motion. So what I recommend you do now is have a look at video number 2, circular motion, and then the gravitational fields topics, which links very closely to circular motion. These are on YouTube. Also, you could go to payhip.com and there's very structured lessons, lots of practice questions, exam questions, quizzes, exam tips, and some progress tracking. So do feel free to check that out. See you next time.